Time for section 2.8. This is a section on related rates. Hopefully you have gotten really good at derivatives. You've taken your quiz, you've gotten all your derivative problems now, and now we're ready to move into the part of the semester where we use derivatives to solve different types of problems. And this is the first type of problem. It's called a related rate problem. And what this problem does is we talk about the relationship between different quantities that are moving. So we have some sort of problem that has motion involved or change involved, and then we can use derivatives to interpret those problems. So probably the best way to start is just to jump right into it, and it's to jump right into our very first problem, which says you pump air into a balloon at a rate of 250 centimeters cubed per second. How fast is the radius of the balloon changing when the radius is 100 centimeters? Not centimeters cubed, that's a typo. Radius is just in centimeters. Okay, when we have these problems, we pretty much always start with a picture. And because we're talking about a balloon, we will probably think of that balloon as being a sphere. So here's our balloon. Here's our nice spherical balloon. Here, let's draw a little bottom on it. Okay, so our balloon is a sphere. We of course know that balloons aren't perfect spheres, but for the sake of math and physics, let's just make it a sphere because that's the easiest to work with. Okay. So the question is, how do we want to solve this problem? And what do we know about a balloon that connects these different ideas? Well, if you see that first line, it's talking about the air in a balloon, and that's the volume. And then we have some statements about the radius of the balloon. And so we know an equation that relates the volume to the radius of a balloon, and that is the volume of a balloon is 4/3 pi r cubed. So that's the volume of a balloon. Now, what we might want to do at this point is you might be tempted to just start plugging in radius and volume, and notice you could plug in the 100 and figure out V, but that's not going to be helpful because that's not what the problem is asking for. So what does the problem want? If you read carefully, you'll realize the problem is asking for how fast the radius is changing. And so notice it's asking for how fast the radius is changing. It doesn't want to know the radius. It doesn't want to know the volume. It wants to know how fast is the radius changing. What is that in math terms? Well, that is dr dt in calculus terms. This is a rate of change of the radius with respect to t. That's what derivatives tell you. It tells you how fast things change. You could, if you wanted, also use like our r prime, or our physics friends like to put a little dot over the r. I'm going to shy away from these notations just for a little bit because it's kind of important to know what variable. So how fast is changing, t, time is your variable. So I'm going to leave the dr dt so that we can see that time is what's at play. Okay, so if we want to know how fast it's changing, what I need to do is I need to not look at this equation, but I need to look at the derivative of this equation. So I want to take this equation and I want to differentiate it. So let's differentiate that equation and see what I get. And now that once I differentiate it, then I get the volume. Once I differentiate, the derivative of the volume is going to be dv dt. So as we differentiate, notice we are differentiating it with dt as our variable. So we get dv dt, and then on the right-hand side, we're going to get 4/3 pi, and then we take the derivative of r cubed, which is 3r squared. But again, we're doing implicit differentiation. T is our variable, so we have a dr dt on here. This is just like when we took the derivative of the y earlier. We had y times y prime, or y times dy dx. It's the exact same idea, except it's r, and we get a dr dt. Now this is a much better equation because notice we wanted dr dt, and now here it is. So now if we plug into this equation, so this equation is our new equation. Okay, so let's do that. And to do that, we need to go through and we need to kind of analyze what's going on in our problem. So this equation, you'll notice, has several unknown things. It has dv dt, it has r, and it has dr dt. So those are the different pieces of this equation that we don't know, but once we know them, then we can plug in. Now, one of those, dr dt, is what we want. So that's what we're looking for. So we're not going to plug in for dr dt. We're actually going to solve for dr dt. And dv dt and r we can find just by reading the problem carefully. dv dt is the rate at which air is pumped into the balloon, and that's 250. So 250 centimeters per cubed is going to be our dv dt, centimeters cubed per second. And our r is the radius at the moment we're interested in. So the radius at the moment we're interested in is 100 centimeters. Okay, so now we're ready. We plug all this into our equation, and hopefully we can get it all to work out. So let me just get myself some new space. Let's write that equation down. Let's go ahead and simplify it a little bit as we write it down. dv dt, I'm just going to multiply the 4/3 times the 3 and just get the number 4 all by itself. dr dt, and now let's plug in. So we'll have 250 equals 4 times pi times 100 squared dr dt. And now we're ready to do a little bit of math, and the math is really simple. It's just solving for that equation. And so dr dt is 250 divided by 4 times pi times 100 squared. I guess we could have written 100 squared is 10,000, so I guess we could have written 40,000 pi or something. But let's just leave it right there. And I'm going to plug it all in my calculator and make a number. I actually don't mind if you leave it here, but let's go ahead and plug it in. And I think our number is going to be really small. And the answer is 0.002. That looks good, 0.002. And then what are our units? Well, dr dt, r is radius, so we get centimeters per second. So it's only growing 0.002 centimeters per second. But, you know, that might seem like a really small growth rate, and it kind of is, but at the same time, this balloon is really big already. It's already 100 centimeters large, so that's 1 meter across. I mean, that's a really big balloon, and you're only pumping air in at 250 centimeters cubed, so you're not getting that much extra air in. So it would make sense that by the time the balloon is that large, it's not growing really fast. It's growing at a much slower rate than it was originally. Okay, I want to talk about a couple things that tend to go wrong when I see students do this problem and not get the correct answer. Well, one thing that tends to happen, and this is the big one, is students tend to think of this problem not as a balloon that's growing in size, but at one balloon at one moment. And so they will label the radius, and if I would have labeled the radius, I would have put an R on here, and I probably should have done that before I started. But what the students said is they'll go, oh, I want to label this with a 100, because that's what the radius is. And that's true, that's what the radius is at the moment we're interested in, but our balloon is not fixed at 100 centimeters. The balloon's actually growing all the time. And so then they would come over here and they would write pi times 100 cubed, and then they would be really confused because when they take their derivative, this part all becomes 0 over here because there's no variable left to take a derivative of. So this is an important distinction. When I draw this picture, and by the way, I have a friend who's done a lot of research on this and explored kind of how people think about these problems. There's two ways of thinking about this balloon. We can think of it as one balloon fixed in time that's a given volume and it has a given radius. But mathematicians don't do that. When they write this balloon down, it actually represents what I call a moving picture. And so this is a balloon that's growing. And so if you can vision, this would be a great moment for me to have like some GIF added to my video. But again, This is not professional hour, so that'll have to happen some other time. But you can imagine a GIF where the balloon is actually growing in size. The balloon isn't staying still, the balloon is constantly growing. And so we want to draw not a picture of one balloon, but a moving picture of the balloon as time changes. And so since the balloon is changing, then it makes sense to write an equation that is changing with the variables included. So as I go through, you can see my list of strategies that I wrote at the bottom. And the important thing is to draw a moving picture. So don't draw a picture of the moment, draw a picture that represents the motion involved in time. Now, we can't draw pictures in motion, so you draw one, and you have to use your mind to put the movement on there. So you have to imagine the movement with your own mind. Okay, but draw a moving picture and then label with variables. Don't label with 100, label with R. Let R be the variable. Now, there will be times, and we'll see in just a minute, where we'll have problems that do have things that are staying constant. So for example, in the next problem, we're gonna have a ladder, and the length of the ladder is not changing. So you don't have to put a variable name on things that don't change, but put a variable name with everything that changes as your problem moves. Once you have that variable name, you write your equation, and so there's our equation. And then we take the derivative of that equation, which is what we did over here, which is where we got our 4/3 pi times 3r squared dr dt. And then we take the derivative of the equation, and then we substitute, so plug everything in and solve. What I find tends to be the most challenging part for students is to do the moving pictures and to use variable names instead of constant names. Okay, we are going to do, we're going to abbreviate this section a little bit, and that's just for the sake of the semester. I want you all to know how to do related rates. We're going to skip some of the harder related rate problems just for the sake of working at home and getting to the end of the semester. And I think with all the challenges we're facing, we're going to do that. But we're still going to do enough related rate problems. I think you understand the process. And then if you were to get a really hard one, you could take the exact same ideas we have right now and use them to tackle the hard problems. I think I'll do one hard problem just for fun for us. So what I want you to do is try exercise 2.44 and try exercise 2.45. If you could do those on your own, then you would really be in good shape, and that means you would really understand what's going on. And then I'm going to do exercise 2.47 for us, and I'm going to skip exercise 2.46. So try 2.44, try 2.45. I'll have videos underneath for you to watch, and there we go. So good luck with those.